exams graded by Monday. Maybe sooner, but Monday at the very latest. So let us continue or finish today our lecture 6 on linear systems. We don't have much left. And then we're moving on to curve fitting, which is arguably an application of linear systems. So just a quick review of our Jacobi method. We're not going to be programmed Jacobi method, and I need to change this again. Just a second. So just a quick review of Jacobi method. There are two alternatives to it. You're going to get a homework problem on them, so we're not going to go into details. We have already programmed Jacobi method. And our problem, if you remember, in Jacobi method, it was reminiscent of fixed point method just for systems. So what we did is we manipulated the original system, AX is equal to B, into a form where I have x's are equal to something else based on this AX is equal to B. So it was really algebraic manipulation of this system. And when I do that, I get something like this, xi to the k plus 1. So this is my next iteration for each xi out of the n of them, is 1 over aii bi minus this sum, which is basically sum of all of the coefficients in that ith row of matrix A and the previously computed x's except for the ith one. So by now we know how to program these sums relatively easily, and we did that for Jacobi method. Now, there are ways to actually speed this up. So in this particular case, what I'm using on the right-hand side is my old iteration for my x's, all of them, however many I'm using. So I have n of them, it's a full vector. And I'm using all of the old versions that I have to create my new iteration. And I keep going until the difference between these two iterations is not sufficiently small. Okay? Now, there's one greedier method, which is called Gauss-Seidel, which essentially says, okay, you're using all of your previous or old iteration. However, at sort of ith stage, okay, so when I'm solving ith for xi, there is previous I minus 1 that you already have new estimates for. Because you have just, in this for loop, you have computed them already. So how about using those new ones to speed things up? So it's just a greedy method. Okay? So essentially, at this computing the new stage, it's taking all of those x's that I already have new versions of. I use those new versions. And for the rest, I use old ones. That's all it's doing. Okay? So basically, when I have x1, I don't have anybody new computed, so I'm just using my old iterations. I'm labeling them with k. Okay? However, as I go through, let's say that my I is 5, okay, for xi is 5, all of the ones up to 4 I already have ready from this previous computation. So I use those new iterations, which I label with k plus 1. And for those that I don't have new estimates, I just use the old ones. That's all. Okay. So basically, this method, that's all there is to about this method. And for the very last one, where I already have all of them that are new ones. Okay. So basically, there's just this splitting, and one can actually go to the Jacobi iteration code that we had before and just modify this, modify it to do this, and that's going to be part of your homework assignment. So you already have most of the code in place. You just have to do a modification. The second version, and all of these versions are trying to just speed things up, okay, is doing the following. It's taking, so I have this old and new iteration. And I go and compute my new iteration based on Jacobi, but then I take a weighted average of the two as what I'm going to move forward as my solution. And that's called successive relaxation method. So I have this lambda, okay? And this lambda basically takes a portion of this new that I have as per Jacobi method and a portion of my older iteration and just kind of does a weighted average of the two. So those are two possibilities. We're not going to go into details of analyzing why do these things work and how much faster they work, but they're just alternatives when I have to solve a lot of problems and similar type of problems. I typically investigate which out of the three methods works the best, and that's the one that I'm using for sort of similar type of problems that have to be repeated all over again. Okay. So that's just as a brief review of the methods for solution of linear systems. We have done a lot of them, and we have spent a lot of time doing that because it's a very important problem in numerical analysis. So we have direct type of solutions, which are Gaussian elimination and LU decomposition. We don't really, if we could have this perfect computer that doesn't have round-off error, our solution to these problems would be the true solution. Okay? However, we cannot avoid round-off errors. And for systems that are rather large, like 1,000 equations and more, the round-off error that piles up is basically too problematic. So we need to go into or find something else. It's also a rather slow computation. Okay? So we typically enumerate or say how slow something is based on the number of computations that needs to be done. Literally counting up how many additions or multiplications and so forth I need to do. And in the case of Gaussian elimination, it's what's called O of n cubed, which means that there's somewhere on the order of n cubed, n being the number of equations, of multiplications. So it's some sort of polynomial that has the leading, if I'm just literally counting up how many, O of n cubed means that there's like 6n cubed plus 2n squared, let's say, additions and multiplications that I need to do. Okay. And when I do that, that's a lot. Like if my system is 1,000 by 1,000, so n is 1,000, then n cubed is 10 to the 9. Okay. So that can be a lot. And problem is that in reservoir engineering, I don't need n is 1,000, I need n is million. So the problem gets out of the hand in terms of the time needed for calculation. Therefore, we go to so-called iterative methods, such as Jacobi, Gauss-Seidel, and successive over relaxation. Their accuracy depends on how close do I choose to get to my solution when I'm measuring error. I never really, even in the perfect situation of having a computer without round-off error, I'm not going to really hit precise solution most of the time, but I can get very close. Okay? So that can be even better than too much round-off error that piles up. Okay? But I have some this truncation error because I didn't actually use the true solution formula. I'm just iterating and hoping to get close to my solution. So I have to chop off my formula somewhere. So that speed depends on how many iterations I need to get there, and it can be much faster for n is larger than 1,000. It can typically be much faster. Okay, so basically that is our direct versus indirect methods, and now we're just gonna finish up a little bit more about matrices and something about estimating. We're not gonna go into details, but I do want to mention this because it's important, and that is that not all systems behave well when I'm doing solutions to them. And some of them are so-called ill-conditioned. So let's, first for that notion, I need the notion of matrix norms. So just like in case of vectors, I have norms for matrices. So just to recall that for vectors, my norms L1, L2, and infinity. So for instance, I have L1, L2, L infinity. L2, for instance, for a vector, x1, x2 through xn, it takes square of all of the numbers, sums them up, and takes the square root of them. Okay? And these are a little different for matrices. Something that looks very much like the sum of square of all of the elements, for matrices is actually called Frobenius norm, and there is a reason for that. So this norm is so-called Frobenius, and it's kind of the simplest one to compute. I just take square of all of the elements. I have two dimensions to this array, so I have to do a double sum in order to compute the norm, and then I take the square root. This is not, however, a direct generalization of the 2 norm for matrices, even though it looks like it. Okay? The definition of a norm for a matrix is as follows. Conceptually, I know that my matrices, when I take matrix n by n, I can multiply that matrix with a vector n by 1. And when I do so, I get another vector of the same size. Is that correct? So kind of every matrix maps, n by n matrix, maps vectors of size n to some other vectors of size n. And therefore, that's actually a linear transformation, a linear function that just works on vectors. Now, we use that for matrices a lot. So for instance, if you ever play video games or do any kind of visualization, in order to stretch something, squeeze something, like an object on the screen, or rotate it, all of that is just successive matrix vector multiplication to get you new locations of this rotated object. Okay? Those operations all have their representative matrices that stretch objects, squeeze objects, rotate them, and so forth. So any matrix can be shown to be, is actually a function that maps vectors to vectors. So when I have that in mind, my matrices are actually functions of vectors that work with vectors and map them to other vectors. Then the way we actually define norm is I take all of the vectors of size 1. So they're all on a sphere. They describe a sphere of radius 1 in my coordinate system. I take all of those vectors and I map them to their resultant vectors using that matrix A. Okay? So for all of the x's that are on the sphere of radius 1, which is what this is saying, I look at where are they mapped to. So let's say that I was stretching all vectors 2 times, then this sphere would go from radius 1 to radius 2. Okay? And stretching something 2 times is really multiplying it with a diagonal matrix that has 2 on diagonal. Okay? That's all. So that's that type of thing. So I would go from everybody on the sphere of radius 1 to sphere of radius 2. Okay. So what I actually estimate to be a norm of the matrix A, in 2 norm of a matrix A, is the maximum of all of these mappings, wherever they end up being. Which, as you might imagine, for this diagonal matrix, it's a simple thing to see where things go. But for something more complicated, it's not so simple. So 2 norm is actually a little difficult to compute. There are numerical ways to do it, and we will have them programmed in Python, but we will not be actually computing 2 norm of matrix A by hand. However, 1 and infinity norms are actually relatively easy to compute. So if I have matrix A, so let's say this 1, 4, 5, 2, 5, 2, 3, 6, 2. Okay? So what 1 norm is I look at J's. So J's are my columns. Okay? So for every column, I sum up absolute values that I see in that column. Okay? And I look at the maximum of those sums. And that's my 1 norm for matrix A. And for infinity norm, I do the same, but I just go row-wise. So let's actually do that. And then I will need my condition number for matrix A will actually be in any norm, norm of A times norm of inverse of A. Let me just shush my messages. Okay, there we go. So let's actually do an example. My condition number of A is norm of A times norm of inverse of A in any norm. Okay? So let's say that I have my matrix A defined as this, and I give you that this is the inverse. Could you quickly compute norm 1 of A, norm 1 of A inverse, and then compute the condition number? Take a piece of paper. So what is my norm 1? I go by columns. So in every column I take absolute values and sum them up. Okay. So norm 1 here will be maximum between 1 plus 4 plus 3. So what is the sum of that? 8. 2 plus 5 plus 2, what is the sum of that? 9. 3 plus 6 plus 2, what is the sum of that? 11. So between 8, 9, and 11, which one is the largest number? 11. So norm 1 of A is 11. Okay. So now do the same for A inverse. So here's the definition, and this is actually the same matrix right here, and it's inverse. So this is the norm 1. So I sum up absolute values, right? And for norm 1, I go column by column. And for norm infinity, I go row by row. So for norm 1, I'm going to sum up absolute values here. And yes, Python has all of these things programmed. Do you remember what was the name of the function? Norm. The name of the function was norm. Question is where was it? Which package was it in? Which module was it in? NumPy.linalg, if you remember that one. So it's NumPy, but you have to call it as np.linalg.norm. And if you forget, Google it. That is a verb. Or whatever other search engine. So this is actually computed in norm 2, in Frobenius norm, I'm sorry. So did you get the norm of A inverse? Norm 1? 19 over 3. So then the condition number will be 11 times 19 over 3. Okay? So what does that mean? Right? Very good question. So I will get slightly different numbers for condition number or norm, depending on the type of norm I use. And for the most part, it doesn't really matter that they're off by 5 or 6 or 7, or they're off by a smaller number, like smaller multiple of each other. The way we look at the condition number is that if it's really large, and when I say really large, like 10 to the 6 or 10 to the 7, that's actually telling me that there is a problem, or there will be some more numerical issues when I'm solving this system. Now, technically, there's a theoretical result telling me the following. If I change, so I expect my system is stable. If I slightly change the coefficients in my system, like coefficients of my matrix A, I expect that the resulting solution to AX is equal to B is not going to be very different from the previous solution. So let's say that I have solution to AX is equal to B, and then I change A ever so slightly. I just twist a couple of coefficients there and change them by 0.01 or something like that. And that's essentially equivalent, if you remember that piping things through reactors, right? Coefficients of my A were actually related to the radii of the pipes in my system, right? So they're related to some physical properties of my system that I'm solving. So I expect, naturally, that if I change radius of my pipe slightly, you know, from radius 1 inch to radius 1.1 inch, I should not have the system behave very differently. However, sometimes they actually do. And part of it is from the system design, because ultimately coefficients in that matrix that I'm solving come from the design of who is connected to who. And I want to avoid bad design. So basically, this expectation that my solutions to slightly changed systems are just slightly different from the previous solution is actually stability of my problem. Okay? Now, that is mathematically, actually, there is a result when I'm solving systems AX is equal to B, then I can actually see that this difference between my two solutions, normalized by the initial solution, is less than or equal to condition number of A times this difference in A, normalized difference in A. Which, if I have a very large condition number, might go through the roof. Okay? And that's a problem. So I want to avoid systems that have very large condition number. Let me give you an example of how that looks like. So here's a system. And one classical example is actually called van der Monde matrix, where you're going to get those, and we're going to see an example of where we get that. But let's just do this one. Okay? Let's look at A. Okay, so my A is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? And let's compute condition numbers and solve AX is equal to B is given over there. And my C is only slightly different. There's 9.1 here instead of 9. That's the only difference that I have in matrix C. So I expect solutions to AX is equal to B and CY is equal to B to be close. Okay? Let's try. Unless this Python business is very optimized to catch that, we will actually see some trouble. So let's fire up our Python. So I'm going to import numpy as np. And I'm going to define as np array 1, 2, 3, 4, 5, 6. And it's that matrix that I type in when I don't know what to type in. So that matrix is actually bad. 7, 8, 9. And my B is and then I also want to, so my X is NP solve A, B. Oops. There's no, is it lineal solve? Yep, that's it. And I can already see that something's really odd with my X. I shouldn't, from those coefficients, I shouldn't be getting something like that. Okay? Now let's try to just ever so slightly change. So I'm just going to copy everything. And I'm going to change this to C, and I'm going to call the solution Y. So I'm just going to change this to 9.1. Let's see what does Y say. It's also pretty wild, but I'm actually getting a pretty close solution. Oh no, because I'm solving for A. So I went from 10 to the 17 back to 700 or 1,000. So the only change I made was from 9 to 9.1. Look at the difference in solutions. So the only change I made is okay. So the solution shouldn't behave that badly. Okay? That is an ill-conditioned matrix. Let's actually indeed confirm the condition number. I'm forgetting inverse. Is inverse INV? Ningyu, can you check? Or I can probably do. So it is INV, okay. But condition number should be conned, right? So we can see that the condition number is 10 to the 16. Okay. Basically, my matrix is almost having no inverse. It's very close to not having an inverse. And that typically causes pretty bad instability. Okay. So if I have a matrix like that, I have to redesign my system. Okay. Because solving over and over and over, especially large systems, is going to bomb. Okay, I'm not going to be able to do solutions. There's an entire sort of branch of linear algebra called preconditioning. And there are people who spend during their PhD how to optimize and go around these problems, because I often have situations where I can't necessarily avoid it. Okay, so that's just for you to know. So sometimes if you have solutions that act really weirdly, maybe it's the matrix A and something needs to be done about the design. Yes?
Do you think the condition number has to be less than 10?
So I would generally say that the condition number up until to the 10 to the 4 is okay. 10 to the 4, 10 to the 5, roughly. Every problem is slightly different, and there's no like precise line. But 10 to the 16 is out of the bag. Okay, that much is true. Partly because 10 to the minus 16 is my machine epsilon, if you remember. So round off errors are going to kill me on this, whatever it is that I try to do. Okay, all right. So another bad system, and this is just for your information, is this given by matrices that have this van der Moor matrix. So if I have any number where I have a square of x1, x1, and 1, so basically coefficients wildly differ. So if my x1 is 10, I'm going to have 100, 10, and 1. And that I start getting orders of magnitude differences between my coefficients, and that's going to often result in a badly conditioned matrix. And actually, a very typical way, if I wanted to interpolate a certain set of values with a polynomial, so if I'm looking for a polynomial that has p1x to the 4 plus p2x to the q, that actually fits certain data, okay? If I actually say, hey, let's find, so basically P1 200 to the 4 plus P2 200 to the cube plus P3 200 to the square, and so forth, has to be equal 0.746. I'm actually going to get that van der Moor matrix. So even though interpolation of a number of points where I'm actually trying to fit a polynomial that fits certain data, it's a problem that I could naturally describe with linear systems and try to solve that. We typically don't, because the matrix that corresponds to the problem is really badly conditioned. Okay. So I'm not actually we're not gonna, technically you could just type in these coefficients and try to solve for this polynomial, and you're gonna get the condition number that is pretty bad, just like this before. Okay. So as a review, linear systems of linear equations are very common in science and engineering, and college football apparently too. This is a comment made. So a lot of times to do various predictions or to deal with the lots of data, which you do a lot of like statistics. When you do any sports, this is not just college football, it's just that it tends to be the dominant sport at UT. Then you actually solve a lot of linear systems, both for prediction, manipulating the data, and so forth. So it's something that is really, really omnipresent from engineering to any other domain. So we often have to solve for systems, and direct methods are those that are represented by Gaussian elimination and LU composition. And iterative methods are Jacobi, Gauss-Seidel, and successive over relaxation. So in all cases, I have to choose the method judiciously. If I have smaller systems, I will go with Gaussian elimination. If I have larger systems, I will go with iterative methods. And in all cases, I do have to sometimes pay attention to the condition matrix of the condition number of the matrix and see whether actually my problem is well posed. Because if I have to constantly solve it, I might have numerical issues. So that is all that we're going to do for linear systems, and we're going to start a new lecture today. That is essentially an application of linear system and is called curve fitting. So my problem of curve fitting, so this is our sort of progress as we go. We're today going to finish curve fitting. After that, I'm going to jump to ordinary differential equations. We might do a little bit of numerical integration if time permits, literally one lecture. So I hope to get there. If not, we're going to finish with ordinary differential equations, which differential equations are your favorite topic, right? That's what I heard. No? No. So curve fitting is the process of finding a functional relationship that fits the data that I see. Most often than not, we don't have any measurements that we do. They don't necessarily come wrapped with a bow saying, well, this is, by the way, the functional relationship between these data, right? Or this is the function that models them. We actually have to go and look at the data and discover. And sometimes we actually have sound science principles that tell me what that relationship should be. So for instance, if I have flow in a pipe, and that flow is laminar or even turbulent, I do know solutions to flow in the pipe. Regardless, especially as I do have solutions, especially for the laminar case, that's what you're going to do in your transport phenomena. For turbulent case, that's a little more problematic. And for those, I actually have to analyze a whole lot of data and try to find the fitting parameters so that I can actually have a predictive relationship. Now, what does that mean? And we also want to put this prediction of parameters from data on some principles. And that's where actually curve fitting comes into play. So let's say that you have any data. Now, data will just be sometimes scattered. So let's say that I have this example up here. Now, this data, I could attempt to, what I mentioned is interpolation. So interpolation is attempting to fit a polynomial that goes precisely through each data point that I have. And that is fine when you have relatively simple data sets. But most likely than not, you're actually going to have a cloud of data. And those measurements, you actually know that they have errors themselves. Especially in petroleum engineering, where a lot of my measurements are averaged over a foot of rock. Okay? When I do well logging, I do measurements every 1 foot or half foot. Either way, I am averaging this much of rock. And I'm literally knocking on the rock and hearing the response. And there's a whole lot that can go wrong in interpreting those results. And there's a whole lot that I don't know, but I'm assuming I know while I'm interpreting those results. Okay? So there's one thing is knowing the flow through a pipe, but flow through a porous medium, I have exact relationship or exact equations that govern it, but they're not easy to solve. And maybe I don't even know the description, the full description on my rock. And even if I do a lot of X-ray imaging with micron size knowledge, so I can actually come up with that description of the rock. But I have it only for this small of a sample that I took out of the reservoir. What about the rest of the rock that is actually still in the reservoir, right? I don't have the description for that. So there's a whole lot that I have to project or assume that I know, based on some measurements and some possibly computation, possibly experimental measurements that I make in the lab. Okay? So in those cases, I have to look at the data and interpret the data. And this is where curve fitting comes into place. And I might have this cloud, and I know that I have some error in the measurements, so it's better to kind of try to strike a line, a trend through my data that is close to everybody, or attempting to be as close to all of the points that I have as I possibly can be, without necessarily going through all of them and visiting all of them. Yeah. So that is actually curve fitting or so-called regression. So here are some examples. Here's an example where actually interpolation or curve fitting does rather well. And there is a capillary pressure relationship, and there's so-called Van Genuchten model, which is a functional relationship. And I can see that my model, which is the line, is pretty close to the experimental data. I'm doing a little better for this higher water situation, and a little less so below. Does everybody know what drainage is? Capillary pressure saturation curve. Should I review? So basically, if I have a piece of rock, and let's say that my rock is water wet, so my water preferentially wets the surfaces, I'm going to first saturate the rock, such as typical sandstone, silica grains. It's water wet. And I'm going to saturate it with water first. And then I'm going to try to displace that water, say, with oil. this rock. And while doing so, it has to displace water. So I can do so because my bedding fluid is preferentially bedding the surfaces and preferentially residing in that pore space. I can do so only if I have enough pressure. And the pressure is actually the pressure difference between my oil phase and water phase, and it's called capillary pressure. That interface between two immiscible fluids can support a pressure difference, and that's called capillary pressure. So that's what I can measure in the lab. I literally measure pressure in both phases, and I can see that difference. So as I'm increasing the difference, I can push more water out with my oil. So I'm draining the bedding fluid, I'm draining the water. And I can go down to pretty low saturations. Okay? Up until actually, technically speaking, this was rescaled to 0. Technically, there's always some residual left behind. Okay? Now, that's basically what my fluids are doing in the reservoir. Then as an engineer, so this is something that naturally has happened during the migration of oil in subsurface. But then as an engineer, I'm going to come in with a water flood to push that oil out. Okay? That's called imbibition, or forced imbibition. So I'm going to actually push more water to actually go back here. Okay? So that's when you have this so-called drainage imbibition relationships that we are studying a lot in order to know how does displacement in my reservoir happen so I can actually manage it. Okay? So this is where our interest in this capillary pressure saturation curves works. And what I'm measuring is just a fraction of water in my pore spaces. If I'm in the lab, I can literally bathe the rock and figure that out, okay, if I have the starting point. So that's essentially the measurement. Now, this is the model where I can either fit, this is curve fitting, but I could actually also just interpolate this data. That is fine. However, I often actually have measurements done. So let's say that I'm in my new reservoir, and over the length of the reservoir, I'm going to take the samples of my rock as I go down. And let's say that most of it is sandstone or sand for simplicity. I'm going to take samples and I'm going to take them to the lab, and for each of them, I'm going to measure porosity and also permeability. Literally, permeability is ability of my rock to push through fluids. And that's just one fluid in this case. And that's also a lab measurement that you're going to get to in petrophysics. So now I have, let's say, 1,000 samples in my reservoir. And they have different porosities. Porosity is the void fraction of the rock. Between 5% and 25%. That's typical sandstone range. I will get a cloud of data. I cannot interpolate the data. I cannot visit every point here and try to fit some polynomial that goes through all of them. Okay? There are different types of samples. Okay? But I'm trying to characterize them in order to describe my reservoir. And that's where I would like to fit a model such as this line that gives me a functional relationship between permeability and porosity. Why? So I can predict what's happening for some sample that I don't have, that I didn't take out. So for any other place in my reservoir, I'm going to use that function to predict. And we have accumulated, and each company has libraries and libraries of these measurements that you can kind of draw from a similar reservoir, okay, when you don't know. So this is where curve fitting is important. So let's try to fit the simplest possible relationship. Okay? And that is going to be a straight line relationship. So if I have data like the one shown, the dots shown here, okay? These are my data points. This line here, it's a very good question. What is the best line to fit through and how do I get it? So one first thing that I want to evaluate, for every point, so let's say that somebody gave me the line, and I want to see how well is that line doing. So what I'm going to do is I'm going to look at the error for each of the points that I have. I know the point, it's x, I, y, I. I have an array of them. Okay? And I'm going to look at this description. So if I have a description of the line, that line has a description such as y is a0 plus a1x. That's a functional relationship describing a line. And I have two parameters, A0 and A1. So basically, I'm going to look at the difference between this point that I have. Let's focus on the second one. And the prediction. And prediction is actually just taking this x is equal to 2 and plugging it into this relationship. So the difference, or the error, is basically my actual value y minus what this line would predict that the value should be. And when I look at the different points, such as this one here, I can see that the difference between the actual point, or y of the point, and the prediction, which is this high up, is slightly larger. Okay? So I have to figure out, for all the points that I have, how do I minimize these errors that I have between the prediction and the actual points, and better yet, how to come up with A0 and A1 so that my error is minimum. And what we actually minimize is not just the error itself, but actually square of the error. Okay? So I take, and there's a reason for that we're going to get into, but not, I don't think, today. So basically, I'm going to take this error between all of these points and their predictions, take the square of it, and sum it all up. And the sum of squared errors is what I'm going to try to minimize, or try to find A0 and A1 to minimize it. Does the objective seem like a reasonable one? Yes?
Why do you square it?
So the reason to square it is the following. Thanks for asking. So let's say that I have something like this. So I have 4 points, right? So if I actually take this line, so this line, okay, error here is negative, error here is positive. And it would look like this line is a close fit to all 4, okay, because these errors actually cancel out. So squaring avoids canceling out of the error. Because in this particular case, I could take this line, and this is the error, and I could take this line, and it's the same error, and in both cases, I'm actually canceling the error out, and I'm not the best fit for all of these 4 points. Okay?
Why don't you just do the absolute value?
So absolute value has another issue that I can explain next time, but basically then squaring gives me the best behavior in finding the result.